Yeah, so please, dear Peijian, the floor is yours. So yes, now we see your screen. Yes.
Thank you, Johan, for organizing this symposium. It is my pleasure to share our recent work on leaf area uh, calculation. Today, my topic is about the theoretical and empirical conditions for validating the Montgomery-Koyama-Smith equation in estimating total leaf area per shoot. This is outlined. Firstly, I will introduce two geometrical equations for calculation of leaf area. One is for calculating individual leaf area, and another is used for calculating the total leaf area per shoot. Secondly and thirdly, I will show validity of those two geometry equation. And fourthly, I will show a geometric series hypothesis for biological size distribution based on leaf area calculation. Uh, Fifthly, I will introduce the theoretical conditions for validating of the Montgomery-Koyama-Smith equation based on the geometry series hypothesis. Finally, 2 points of discussion will be done. Okay. Just for a moment. Okay, I just. Uh, this panel show the Montgomery equation. Here A represents individual leaf area, which is assumed to be proportional to the product leaf length and leaf width. Here K, this equation, okay, here K is the proportionality coefficient referred to as the Montgomery parameter. The second geometry equation was proposed by Koyama and Smith in 2022 for calculating total leaf area per shoot. It takes the form like this, okay? Here, AT means the total leaf area per shoot, and LKS represents the sum of leaf widths in a shoot, just like it. And the WKS, okay, represents the maximum individual leaf length in this shoot. Here also there is a proportionality coefficient for this equation. For the first, sorry, maybe no. We have used the 5 species of plants to validate the Montgomery equation. Here, we use the first kind of definitions for the leaf length and leaf width. Here, leaf length is defined as the straight line length from the leaf base to leaf apex. And leaf width is then defined as the maximum distance between the 2 points on the leaf edge that forms a straight line perpendicular to the leaf length axis. Okay. For each species, we sample more than 300 leaves. here is the fitted fitted results. To normalize the variables in Montgomery equation, we log transformed the equation like this. Okay, we can see it becomes a very simple linear equation with the slope being 1. Okay, we just need to estimate the intercept like this. Here we can see the observations like the small circles all around the regression lines. Okay, and we find the Montgomery parameter, namely the coefficient, the proportionality coefficient in the Montgomery equation reached between 1/2 and pi4. Okay, which corresponding to extreme leaf shapes, namely the triangular leaf and elliptical leaf. Okay, we test another definitions for the leaf length and leaf width. In practice, okay, it is somewhat difficult to find leaf width in coefficient approach. Namely, this line should be perpendicular to the leaf length. So for some plants with lobed leaves, we can define the W, namely the leaf width, as the interapical straight line distance. Okay, and we just compared the goodness of fit using the conventional approach with the interapical approach, namely define the W here. Okay, we found that there was a negligible distance in the goodness of fit between the two approach, namely, okay, define the leaf length as the maximum distance perpendicular to the leaf length axis, and okay, the another definition for the leaf length, okay, namely the interapical apical length. Okay, here the third kind of definitions for the leaf length and the leaf width. Okay, as we know, the true leaf length should be the measurable. I mean, the first order wing. Its length. It should be covered for some leaves which are not perfectly bilateral symmetric. Okay, so we use the image J to to measure the mid-rob length, and we compare this approach with the conventional approach. And we also found, this is in the on the left column, we show the mid-rob based approach. On the right column, we show tradition approach. Okay, it is just the two species. Okay, we found that there was a negligible difference in goodness of fit between two approaches. So we can draw some conclusion as follows. The Montgomery equation is valid for calculating leaf two-dimension area for different leaf shapes. It doesn't require the leaf width axis to be perpendicular to the leaf length axis. Whether the Montgomery equation is valid mainly depends the extent of the similarity across different leaves from the same species or cultivar. This equation can be extended to the area calculation for other biological structures, such as patterns, stoma, even for insect wings. Okay. Now, let us turn to the Montgomery-Koyama-Smith equation, which is used for calculating the total leaf area per shoot. You can say, okay, on a plant, we summed the leaf areas for different leaves. We get it, okay, and we also can get it is LKS, which means the sum of leaf wings on in this shoot. And the WKS is just defined as the maximum individual leaf length. To get this, to test it is validity and estimate the proportionality coefficient, namely KS. We also we also use a log transformed version for this equation, just like this. We can say it also reduced to a simple linear equation with sleep being unity, and we just need to estimate this intercept. Okay. However, for testing the validity of this equation, we use another equation, namely power law equation. Here it is form. Okay, we can find it. Additionally, has a parameter alpha. Here, alpha is a power. If alpha is equal to 1, we can say this power law equation reduced to a proportional relationship, namely the Montgomery-Koyama-Smith equation. We also log transformed this equation. Okay, sorry, should be a typo. Okay, it is PLE. Okay, it was written as like this. Okay, we find in this equation has a intercept and the slope. Okay, we check whether the 94% confidence interval of the slope include 1. If it include 1, it can validate the Montgomery-Koyama-Smith equation. Okay, if it doesn't include 1, it is an invalidated MKSE, or it at least tell us that okay, the Pallow equation is slightly better than the MKSE. Okay, we use 3 bamboo species to test it. Okay, we can say, okay, it is also they are all herbaceous. Okay, bamboo. Okay, maybe a dwarf bamboo. Okay, here is MKSE fit result. Okay, in panel A. Okay, it is about the proportional relationship between AT and the product of LKS and WKS, namely the MKSE. Panel B, okay, is a fitted result, result of Pallow equation. Let us check. Okay, it is 95% conformation interval of the slope. Here, the upper bound of the CI was smaller than 1. It indicates that, okay, PLE doesn't support the MKSE. Okay, the same case occurred for other 2 bamboo species. We can see, okay, like this. Okay, the upper bounds of the CIs were also smaller than unity. Okay. To test the generality of the MKSE, we use Magnolian, okay, species. It's a tree. We use more than 300 flowers to calculate the total area, and we also use the same way to calculate LKS, WKS. Okay, here LKS means the sum of tepals on a flower, and WKS means the maximum tepal length. There is need to note that for Magnolia species, it is hard to distinguishing patterns from sepals. Okay, so we use tepal to call them. Okay, in pen A, it is fitted result from MKSE, and in pen B, okay, it is fitted result from using PLE. That means the relationship between AT and LKS multiplied by WKS doesn't hold true, at least for this example. However, when we sample, okay, some okay crab apple cultivars, okay, just like we calculated the pattern, total pattern, means corolla area, and the individual pattern area. We use this equation in the middle panel. Okay, it is about the fitted results using Montgomery-Koyama-Smith equation. On the right column, okay, it is fitted results using power law relationship. Okay, so we can see it is slows include one. It validates, okay, the MKSE. Okay, but for the another three cultivars, okay, it is just so. Okay, now we can get some conclusion about MKSE. The Montgomery-Koyama-Smith equation holds true and basically reflects the relationship between total leaf area per shoot and the product of some leafed wings and the maximum leafed length per shoot. Okay, the power law equation slightly outputs the MKSE in the goodness of fit. For the three bamboo species and magnolia species, the numerical value of the scaling exponent, namely the slope of the AT versus LKS multiplied by WKS, is significantly smaller than unity. Okay. For the six malus cultivars, the numerical value of the slope is approximately equal or slightly high, greater than unit. Okay. Now let us turn to the geometric series hypothesis for the biological size distribution. For the size distribution of individual biological structure, for example, the leaves on the shoot, the tepals on a flower, and the storm in a in a photo, the variation in size between two adjacent structures can be regarded as a constant. In that case, the geometry series hypothesis is probably potential happen for reflecting such variation. However, the geometry series hypothesis has been seldom tested to describe the size distribution of biological structures. Okay, for the geometrical series, we all know it is a general item like this. Okay, and the cumulative area of the first J terms is like this. Okay, we all in China at least we learned in the middle school. Okay, no problem. For the sorted leaf area sequence in a ascending order, each term can be expressed as this, okay, as mentioned above, where AI and I can be regarded as the dependent and independent variables, respectively, and Q and A1, namely the first term of the GS, okay, can be regarded as the model parameters. So for the n pairs of observation of I and AI, we can use non-linear least squares method to be estimated them. Okay. We use mean absolute percentage error. MAPE is acronym between the observed and the predictor cumulative leaf areas for each shoot. We use it to access the goodness of fit when we assume the leaf area distribution follows geometry series. Okay. Sorry. As a rule of thumb, okay, if MAPE is more than 5%, we can say the goodness fit is better. We also use the Magnolian species and the six cultivars, other flowers to test it. And we use a bamboo species. This bamboo species has so many leaves for each shoot. So we scaled each shoot. I must thank my students to do this work. Okay. Here is the fitted result. Okay. The open small circles are observations for the cumulative areas of the first J items, and the red line represents the predict values. In fact, they should also sketch the points rather than a slide, but to show it is cleanly, so I use the lines. Okay. So we can say the MAPE is significantly smaller than the 5%. This means for the flowers, okay, it works well. The same result occur for the six cultivars of malus. Okay, so we can say that's good because for each flower, there are only 5 patterns. It is very important to derive the following the hypothesis. Okay, it is the result. All the flowers, the MAPE were smaller than 5%. Okay, but for the bamboo species, it is just so. We can say MAPE, most APE are larger than 5%. However, about more than half of bamboo culms, okay, others MAPE were small than 10%. Okay, it's just good. But for the cumulated, okay, the leaves cumulative areas, the geometric series hypothesis basically holds true, at least for this bamboo species. Okay, this is there are theoretical conditions for the validity of the Montgomery-Koyama-Smith equation based on the geometry series hypothesis. Okay, here I just say the conditions has a condition. That's the leaf area distribution should follow geometric series hypothesis. Okay, the first one is leaf length scales automatically or isometrically, both can with the leaf length, namely like this, okay? The number of leaves per shoot is a constant across shoots. Of course, it doesn't hold true for the observation. However, it holds true for malus flower. For malus flowers, many malus cultivars, the number of patterns, the number is 5. Okay, there should be a very small variation or no variation in the commercial common ratio of the geometry series. If those 3 conditions do not hold true, we can demonstrate that the power law equation is better than the the Montgomery-Koyama-Smith equation. Here are the proofs. Because the limitation of time, I don't show them in detail.
You have enough time, Peijian. You have enough time if you wish.
Okay, but there are many slides. Okay, sorry. So we can it. Okay, yeah, like it.
No. You have enough time. Please,
Yeah.
please take all the time you need. Take all the time.
Okay. So, okay, let's say this sequence. Okay, here AI represents the leaf area sequence in ascending order, and Li and Wi are also ascending sequence. Because the Montgomery shows this, and there is a scaling relationship between leaf vents and leaf lengths. So we can rewrite it like this. Okay, we defined a W as the function of Q and N. We can get this. Because for a ascending order sequence, the common ratio Q is greater than 1. So Q to the power N minus I also is also greater than 1. So we can get WQN is smaller than 1. We do some more. We derive some conclusion like this. Okay, we define the G and the H. Okay, we can find those 2 functions are increasing functions of N. Okay, here we assume that the Q is a constant. Okay, we just consider the changes. Okay, of W of W. Okay, so because the 2 functions are increasing function of N, and we also say W is a decreasing function of N, which holds at least for this limitation conditions. Okay, we can just use the real okay, the derivative of W with respect to N can get those results. Okay, so we can derive that the power should be small than 1. Okay, because we fixed Q to be a constant. Now we see another example. If N is a constant, let us say WQ. Okay, in a similar way, we can prove that WQ is a distant function of Q. when A is a constant. Okay, here A is the scaling exponent of leaf width to leaf length. Okay. We can see MKSE appears to be more suitable for calculating the total topel pattern area per flower that has a fixed number of the topels or patterns. The hypothesis of MKSE, the total leaf area per shoot is proportional to the product of LKS and WKS is not better than the allometrical relationship, assuming there is a allometrical relationship between the two variables in calculating total leaf area per shoot. Okay, given that, okay, just the three conditions, namely, leaf width doesn't scale the automatically or isometrically with the leaf length. The second, the number of leaves per shoot has a large variation across shoots. All the common ratio of the geometric series for the leaves per shoot has a large variation under the GS hypothesis. Okay. Here, I need to point out if the leaf area distribution doesn't follow the geometric series hypothesis, the MKSE properly still holds true even though the number of the leaves has a large variation across different shoots. Okay, but I don't show this example. Finally, I will given us 2 points of discussion. Whether there is a significantly correlation between the Montgomery parameter, namely the proportional coefficient of the Montgomery equation, which is used to calculate the individual leaf area, and the proportionality coefficient of the Montgomery-Koyama-Smith equation, which is used to calculate the total leaf area per shoot. Whether there is there is relationship. Does the proportion relationship still holds true for from 2-dimension to 3-dimension measures of biological structures? Using the 6 malus carnivores, because we has each pattern, okay, scaling, we can get it is length, width, and get it is total corolla area, namely the total pattern area. We can get it is Montgomery parameter, namely the proportionality coefficient of the Montgomery. Here, x means this coefficient, and the y represent the proportionality coefficient of the Montgomery-Koyama-Smith equation. We find a very strong linear relationship. At first, I had thought maybe my R programming had some problems. Okay, but after carefully checking it, I find very strong, okay, let's living relationship. Okay, so maybe we need to explain it in theoretical basis, but now this work has not finished. Okay, you can see, okay, there is a proportional relationship between the two coefficients. The second discussion is about, does the proportional relationship still hold true from 2-dimension to 3-dimension measures of biological structures? Here, where new work, Carl and Johan are very important collaborators or co-authors. Okay, We use the jingle biloba scleral testing. Okay, we can simply call it is seed, although it doesn't mean a true seed. Okay, we measure every seed, its length, width, and thickness. It is well known that for a standard ellipsoid, it is volume is equal to 4/3 multiply pi and multiply three semi-axis. Okay, three semi-axis can be expressed as the half of seed length and half of seed width and half seed thickness. Okay, so we can get it is theoretical volume. Okay, and we use graduated graduate cylinder, okay, to measure it is observed volume. We checked the relationship between theoretical volume like this, okay, like this VE, okay, and the observations of volume use water replacement, okay, based on the cylinder, okay. On the left column, okay, on the left column, we show, okay, others fitted result using linear regression. We can see the confidence interval of the slope include 1. It uses three trees of ginkgo biloba and it use another 12 ginkgo biloba trees, okay, because we carry out two different samplings, okay. Now let us turn to the possible future work. From a group similar two-dimension geometry, whether it is area equal to the product of two one-dimension measure that are perpendicular to each other or not, and do not align on the straight line. For any a group of similar three-dimension geometry, whether it is volume equal to the product of three, I'm sorry, it should be product three one-dimension measures that are perpendicular for each other or not, or do not on the same plane. The Gillis equation, namely a polar coordinate equation for general biological geometries, is promising one solving the about two question given the two-dimension area and the three-dimension volume can be easily calculated based on the Gillis equation. Simulation and empirical studies can be considered in future. Now, let us see this Chinese translator version for the Thompson's on growth and form. This is the book, okay, the cover page, okay. Thompson in 1917, okay, proposed a principle of similarity. He assumed that area is proportional to the square of its length, and its volume should be proportional to its length to a power 3. However, from our recently work, it might be incorrect in biological structure. At least the prediction accuracy derived from this principle is weak than that of the Montgomery equation in two-dimensional geometries. Okay, here in the in the left bottom pattern, okay, we show a result, a fitted result between the goodness of fit using Thomson's principle of similarity for the area, namely leaf area is proportional to the leaf length squared. It is goodness of fit using root mean square error. Okay, if its value is small, it indicates a good fit. Okay, if its value is large, it illustrates that a large prediction error occurs. Here, X is the coefficient variation of leaf the ratio of leaf width to leaf length. Okay, we can say if leaf width is proportional to leaf length, no problem. Thomson's principle of similarity holds true. However, however, most observation shows that there is no square relationship between leaf length and the leaf sorry, the leaf area and the square of leaf length. So maybe in the future we can test the formula that any three-dimension objects, its volume can be proportional to three dimension measures, others product. Okay. There is some reference for this lecture. I must thank Johan, Carl, Eula, David, Julian, and Dirk for others' invaluable collaboration work with us on this topic. And I must thank you, my students, others invaluable, okay, the sampling work and data acquisition, okay. Thank you very much for your attendance, okay.